Picture a flash of light so brilliant it outshines entire galaxies, a beacon of unimaginable energy tearing through the void of space at the speed of light. These are gamma-ray bursts, the universe's most colossal explosions, born from collapsing stars or merging neutron stars, ripping through the cosmos with a kind of power we can scarcely comprehend. And yet, what if I told you the most astonishing ones aren't happening nearby, or even in our cosmic neighborhood, but billions of light years away, from a time when the universe itself was still in its infancy? These aren't just distant cosmic fireworks, they're messages from the edge of time, carrying secrets about how everything began and how it might all end. Today, we're embarking on a journey to explore the most distant gamma-ray bursts ever detected, events so ancient their light has traveled for more than 13 billion years to reach us. That means we're witnessing explosions that occurred when the cosmos was barely a toddler, a chaotic and mysterious era filled with the first generations of stars, the birth of galaxies, and the raw, untamed forces shaping reality itself. These aren't just scientific curiosities, they're time capsules offering us a window into the universe's earliest moments, and they hold clues to some of the biggest questions we can ask. How did the first stars form? What were the conditions like in those primordial times, and what do these titanic bursts tell us about the fate of our own cosmic home? So settle in, because over the course of this video, we'll dive deep into 30 mind-bending facts about these incredible phenomena. We'll travel across space and time, from the detection methods that allow us to spot these fleeting flashes to the staggering implications they hold for our understanding of physics, astronomy, and the very nature of existence. Whether you're a seasoned space enthusiast or just curious about the wonders of the cosmos, this journey promises to leave you awestruck, inspired, and maybe even looking up at the night sky with a whole new sense of wonder. Before we can truly appreciate the monumental journey of these distant bursts, we need to understand exactly what they are. So let's start with the basics. A gamma-ray burst is, in its simplest terms, the single most powerful and violent explosion known to occur in our universe. Think of the Sun, our local star, a colossal furnace that has been burning steadily for over 4.5 billion years and will continue for billions more. In the blink of an eye, a single gamma-ray burst can unleash more energy than our Sun will produce across its entire 10 billion-year lifespan. It is a staggering, almost incomprehensible release of power, a cosmic disaster on a scale that dwarfs supernovas and makes even the most destructive events in our galaxy seem quiet by comparison. These cataclysms originate far beyond our own Milky Way, in the hearts of distant galaxies, and they announce their arrival with a focused beam of the highest energy form of light, gamma rays. This beam, traveling across the universe at the speed of light, is like a lighthouse flash from the edge of eternity, and if one were pointed directly at Earth from within our own galaxy, it would be a civilization-ending event. Fortunately for us, they are incredibly rare in our cosmic neighborhood and are instead spotted billions of light years away. Scientists categorize these titanic explosions into two primary types, which point to two very different kinds of cosmic doom. The first are known as long gamma-ray bursts. These are the ones that last a bit longer, from a couple of seconds to several minutes. They are the final, screaming death cries of the most massive stars in the universe. When a star many times heavier than our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity, not into a neutron star but directly into a black hole. As material from the star plummets into this newly formed abyss, some of it is ejected in two powerful, oppositely directed jets. It is these jets, moving at nearly the speed of light and punching through the outer layers of the dying star, that we observe as a long gamma-ray burst. The second type is the short gamma-ray burst. As the name implies, these are much briefer events, typically lasting less than 2 seconds, but do not let their fleeting nature fool you. They pack an incredible punch. These are not born from the death of a single star, but from the violent merger of two incredibly dense stellar corpses, either two neutron stars or a neutron star and a black hole. When these objects spiral into each other and finally collide, they create a new black hole in a fraction of a second, and in that same instant, they too fire off those incredibly energetic jets of gamma radiation. This distinction is crucial because it tells us that the universe has more than one way to create such an unimaginable spectacle. And as we'll soon discover, the most distant, ancient bursts we've detected are almost exclusively the long variety, the fireworks from the very first generation of massive stars to ever exist. Now, the story of how we first stumbled upon these cosmic monsters is almost as incredible as the bursts themselves. It begins not with a grand astronomical mission, but in the midst of the Cold War, high above the Earth. In the 1960s, the United States launched a series of satellites known as Vela, Spanish for Watchman. Their sole purpose was to monitor the skies for the telltale gamma-ray flash of a nuclear weapons test, ensuring that no nation was breaking the ban on atmospheric testing. These satellites were essentially nuclear spies in space, and they were exceptionally good at their job. Then, on July 2, 1967, something completely unexpected happened. The Vela satellites detected a massive spike of gamma radiation, but this signal was all wrong. It didn't come from the direction of Earth, and its signature didn't match any known weapon or natural phenomenon from our planet. The scientists working on the project, led by a team at Los Alamos National Laboratory, were baffled. Over the next few years, more of these mysterious flashes were detected, each one seemingly random in its origin and timing. The data was so perplexing and so potentially sensitive that it was kept secret for years while the team tried to figure out what they were seeing. They knew it wasn't a nuclear test, but they had no other explanation. The true nature of these signals remained one of the biggest scientific mysteries of the era. Were they coming from somewhere within our own solar system? Perhaps from our own galaxy, the data was frustratingly vague. It wasn't until the early 1970s, with more advanced satellites and the meticulous work of researchers like Ray Klebisadel, that the team could finally triangulate the direction of these bursts. The stunning conclusion was that they were not coming from anywhere near Earth or even from our galaxy. They were originating from deep, deep space far beyond the Milky Way. This realization was a complete shock to the astronomical community. Imagine setting up a security camera to watch your front door and accidentally discovering a whole new class of explosion happening in a distant galaxy you never knew existed. That was the scale of this accidental discovery. For decades after that, the mystery only deepened. Without knowing the distance to these events, scientists couldn't calculate their true power. Were they relatively small, nearby events, or were they the universe-shattering cataclysms we now know them to be? The debate raged on until the 1990s, when new instruments, particularly NASA's Compton Gamma Ray Observatory, finally began to provide answers by precisely locating bursts and allowing ground-based telescopes to spot their fading afterglows in other wavelengths of light. This was the key that unlocked their distance, revealing that they were indeed coming from billions of light-years away, confirming their status as the most powerful explosion since the Big Bang itself. What began as a top-secret military project to watch for human conflict had inadvertently opened a window to the most violent and energetic events in the entire cosmos. For years, the true nature of these mysterious flashes was the subject of one of the most heated debates in modern astronomy, a puzzle that split the scientific community into two distinct camps. On one side were those who believed gamma-ray bursts were relatively local events, perhaps happening in the halo of our own Milky Way galaxy. This galactic model seemed to solve a few problems. If the bursts were closer, their required energy output would be far less extreme, making them slightly less baffling. Imagine hearing a loud bang outside your window. your first assumption isn't that it's an explosion on another continent. You assume it's a car backfiring down the street. For a long time, that was the simplest, most logical conclusion for many astronomers. The other side of the debate argued for a cosmological origin, meaning the bursts were coming from far beyond our galaxy, from the deepest reaches of the universe. This was a much more radical and unsettling idea. If these explosions were that far away, the energy required to make them visible across such a mind-boggling distance would be almost unimaginable, challenging the very laws of physics as we understood them. It was the equivalent of hearing that loud bang and concluding it was actually a supernova in a galaxy a billion light-years away. The idea seemed almost preposterous, requiring a complete rethink of cosmic power scales. The debate raged throughout the 1980s and into the 90s, with compelling evidence and clever theories on both sides. The galactic camp pointed to the seemingly random and isotropic distribution of the bursts in the sky. They appeared to come from everywhere equally, which didn't immediately suggest distant galaxies that are clustered in specific regions. The cosmological camp, however, argued that our instruments weren't precise enough to see the subtle clustering that would prove their distance. The stalemate was finally broken not by a single eureka moment, but by a technological leap. The launch of NASA's Compton Gamma Ray Observatory in 1991, and crucially, the Italian-Dutch Beppo-SAX satellite in 1996. Beppo-SAX was the game-changer. It was uniquely equipped with instruments that could not only detect the initial gamma-ray flash, but also quickly and precisely pinpoint its location in the sky with unprecedented accuracy. This precise coordination was the key. For the first time, astronomers could instantly relay the coordinates of a burst to powerful ground-based optical and radio telescopes, which would then swivel to stare at that exact patch of sky. What they found was the afterglow, a fading but longer-lived emission across other wavelengths of light that acted like a cosmic address label. By studying the afterglow, astronomers could obtain a spectrum of the light, which allowed them to measure the burst's redshift, a direct indicator of its distance. The results were unequivocal and staggering. The measured redshifts placed these bursts billions of light-years from Earth, confirming once and for all their cosmological origin. These were not local firecrackers, they were truly universe-spanning detonations. This resolution of the great debate didn't just settle an argument, it completely transformed our understanding of the cosmos, revealing it to be a far more violent and energetic place than we had ever dreamed. But how do we actually know with such certainty that a burst originated from so far away, from a time when the universe was so incredibly young? The answer lies in a fundamental and elegant feature of our expanding cosmos, a phenomenon known as redshift, and it's the single most important tool astronomers have for measuring these immense distances. To understand redshift, we first need to remember that light behaves like a wave, and the distance between the crests of these waves determines its color. Shorter wavelengths appear blue or violet to our eyes, while longer wavelengths appear red. Now, imagine the universe itself is stretching, with every galaxy moving away from every other galaxy as space expands. This is not like an explosion where objects fly through space. It's that the very fabric of space between them is growing. When a gamma-ray burst erupts in a distant galaxy, its light begins its epic journey across this expanding universe. As the light travels, the space it's moving through is also stretching, which has a direct effect on the light waves themselves. The waves literally get stretched out, causing their wavelength to become longer. This process shifts the light toward the red end of the spectrum. The farther the light has to travel, the more the universe has expanded during its journey, and the more its light is stretched or redshifted. Astronomers quantify this shift with a simple but powerful number called Z, the redshift value. A higher Z value means more stretching has occurred, which translates directly to a greater distance, and because light takes time to travel, a look back into a much earlier era of the universe. For relatively nearby events like a burst in a modern galaxy, the redshift might be a small number like 0.1. But for the true cosmic monsters, the bursts from the edge of time, the Z values become staggering. We're talking about redshifts of 6, 9, or even higher. A gamma-ray burst with a redshift of 6, for example, means we are seeing it as it was when the universe was less than 1 billion years old, a mere fraction of its current age. It's a direct line to the past, a way to turn a measurement of light into a measurement of time and distance simultaneously. This isn't just theoretical, it's how we cracked the case on the most distant burst ever recorded. When a satellite detects a flash, telescopes on Earth and in space scramble to find its fading afterglow. They don't just take a pretty picture, they break that light down into a spectrum, looking for the unique chemical fingerprints of specific elements. But in the light from these ancient bursts, these fingerprints aren't in the expected places. The telltale patterns of hydrogen or oxygen are all shifted far into the redder parts of the spectrum. By measuring exactly how far these familiar patterns have been shifted, astronomers can calculate the precise redshift, instantly revealing the burst's profound distance and its epoch-making origin. It's this incredible tool that transforms a brilliant but mysterious flash into a dated entry in the cosmic history book, allowing us to confidently state that we are witnessing the death throes of one of the very first stars to ever shine. And now we come to a true legend in the field, a burst that for years stood alone at the pinnacle of cosmic distance, a record holder that gave us our first clear glimpse into the universe's deepest past. Its name isn't poetic, GRB 090423, a designation that simply marks the date of its discovery, April 23, 2009. But this alphanumeric code belies its profound significance. Detected by NASA's Swift satellite, this flash of gamma rays was immediately recognized as something special, something different. Its light profile was faint and fleeting, lasting only about 10 seconds, but it was enough to trigger the automated systems and set in motion a global race among astronomers. Telescopes around the world and in orbit immediately swung into action, searching for the fading afterglow. The critical breakthrough came from the Very Large Telescope, or VLT, high in the mountains of Chile. Its powerful instruments managed to capture the faint, infrared glow of the burst's aftermath. When astronomers analyzed this light, they found something that took their breath away. The signature of hydrogen in the spectrum was shifted so far into the infrared, it was almost unrecognizable. The calculation that followed revealed a staggering redshift value of 8.2. To grasp what that number means, you have to translate it into time and distance. A redshift of 8.2 meant this explosion occurred when the universe was a mere 630 million years old. Let's pause on that for a moment. The universe is currently 13.8 billion years old. This burst erupted when the cosmos was less than 5% of its current age. It was a time often called the Cosmic Dawn, an era when the first stars and galaxies were only just beginning to illuminate a vast, dark, and mostly empty cosmos. The light from GRB 090423 had been traveling through the expanding universe for over 13 billion years to finally reach the sensors of our telescopes. We weren't just looking at a distant object, we were witnessing a historical event from the universe's infancy, a cataclysm so ancient that by the time its light arrived, the star that produced it had been dead for longer than our solar system has even existed. This record-breaking observation did more than just win a cosmic distance contest. It proved a crucial concept to astronomers, that gamma-ray bursts could indeed be used as probes of the very earliest epochs. The fact that we could detect such a violent event from so long ago told us that massive stars capable of dying in such a spectacular fashion, were already forming and dying incredibly quickly after the Big Bang. The universe clearly wasn't wasting any time. This single data point, this flash from the void, provided irrefutable evidence that the chaotic, energetic processes of star birth and star death were already in full swing, lighting up the primordial darkness with their final, furious acts of creation and destruction. To truly appreciate the journey of that single photon from GRB 090423, we need to grasp the sheer scale of its voyage. That burst of light began its epic trek across the cosmos over 13 billion years ago. To put that almost incomprehensible span of time into perspective, consider that when this light first started traveling, our own planet Earth did not exist. The Sun was still a young star, and our entire solar system was nothing more than a swirling cloud of gas and dust. By the time that light was halfway here, single-celled organisms were just beginning to emerge in Earth's ancient oceans. And for the vast majority of its journey as it sailed through the void, dinosaurs ruled our world, went extinct, and mammals rose to take their place. All of human history, from the first cities to the launch of the swift satellite that finally detected it, unfolded in the last fractional second of that light's 13 billion-year journey. This immense travel time means we are not seeing the burst as it is now, but as it was when the universe itself was in its absolute infancy, a mere 630 million years old. If we compare the entire history of the cosmos to a single calendar year, with the Big Bang at 1 second after midnight on January 1st, this gamma-ray burst detonated around January 10th. The universe was a completely different place then. It was smaller, denser, hotter, and shrouded in a fog of primordial hydrogen gas. The first generations of stars, often called population 3 stars, were beginning to ignite, and their brilliant, short lives were fundamentally transforming the cosmos around them by burning away the dark ages and lighting the first fires in the void. Observing GRB 090423 is the scientific equivalent of finding a perfectly preserved fossil from the Precambrian era. It's a direct snapshot of the conditions in that primordial universe. The fact that such a massive star lived and died so quickly after the Big Bang tells us that the early cosmos was a far more violent and dynamic place than we once imagined. It wasn't a slow, gradual process. It was a period of incredibly rapid and intense star formation where behemoths were born, lived ferociously, and died spectacularly in the blink of a cosmic eye. This single flash of light, therefore, is so much more than a distant explosion. It is a messenger from the cosmic dawn, carrying encoded information about the composition, the structure, and the very physical laws of the universe at a time when everything was just beginning to take shape. These cataclysmic events don't just happen randomly. They require a very specific and frankly terrifying stellar recipe. To create a long gamma-ray burst, a star doesn't just die, it dies in the most extreme way possible. The key ingredient is mass, and an enormous amount of it. We're talking about a true cosmic behemoth, a star that dwarfs our own sun by a factor of 20, 40, or even 50 times. Stars this massive live fast and die young, burning through their nuclear fuel in a frantic race that lasts only a few million years, a mere blink in cosmic time compared to the 10 billion-year lifespan of a star like our Sun. But mass alone isn't enough to create this spectacular finale. The second crucial ingredient is rapid rotation. The star must be spinning incredibly fast, like a cosmic figure skater pulling their arms in to accelerate. This rapid spin is vital because it helps to shape the entire explosion. When such a massive, rapidly spinning star finally exhausts its fuel, the inward pull of its own immense gravity becomes unstoppable. The core, no longer supported by the outward pressure from fusion, catastrophically collapses. In a matter of seconds, it crushes itself down into an infinitely dense point, a newborn black hole. Now here's where the magic, or rather the mayhem, really happens. Not all of the star's material falls directly into the black hole's event horizon. The star's incredibly rapid rotation forces this infalling material to form an incredibly hot, swirling disk of plasma. known as an accretion disk, whirling around the newborn singularity at nearly the speed of light. The enormous friction and magnetic fields within this superheated disk then channel some of the gravitational energy into two narrow, oppositely directed jets that blast outward from the star's poles. These jets, composed of particles moving at over 99.9% the speed of light, are the gamma-ray burst itself. They act like cosmic blowtorches, drilling their way through the outer layers of the dying star before erupting into the interstellar void. This entire violent process is what astronomers call a colossal model, and the accompanying supernova explosion is so immensely powerful that it earns its own special name, a hypernova. It's a supernova on steroids, an explosion that can be orders of magnitude brighter than a typical stellar death. So when we detect a long gamma-ray burst from the edge of the observable universe, we are witnessing the signature of a hypernova, the birth cry of a black hole, and the final, defiant act of a star so massive and dynamic that its death outshines billions of suns. This brings us to a crucial detail that makes these distant bursts visible to us at all, a feature that explains their staggering brightness and solves a major puzzle in astrophysics. It's the concept of beaming. You might logically assume that when a star explodes, it does so in all directions at once, like a gigantic spherical bomb. But gamma-ray bursts are not like that at all. Instead, they are the universe's ultimate example of a focused explosion. The incredible energy is not wasted by being sprayed in every direction. It is concentrated into two incredibly narrow, oppositely directed jets that scream out from the poles of the dying star or merging object. Think of it not as a bomb, but as a lighthouse. A lighthouse doesn't illuminate the entire ocean. It focuses its beam into a single, rotating shaft of light that appears brilliantly bright to any ship that happens to be in its path. For a gamma-ray burst, the collapsing stellar core acts as the powerful lamp, and the complex physics of its rotation and magnetic fields form the lens, channeling that unfathomable energy into twin jets. These jets are astonishingly narrow, typically spanning only a few degrees across. To put that in perspective, hold your fist out at arm's length. The width of your fist covers about 10 degrees of the sky. The jet of a gamma-ray burst is often narrower than that. This beaming effect is the key to understanding their extreme luminosity. Because all the energy from the hypernova is funneled into such a tight beam, the intensity of the light within that beam becomes unimaginably high. It's the difference between using a floodlight to illuminate a whole stadium and using a laser pointer. Even if the laser has far less total power, its focused beam can appear dazzlingly bright at its target. This is why we can see gamma-ray bursts from billions of light-years away. If the same amount of energy was spread evenly in a sphere, it would be so diluted by the time it reached us that it would be undetectable. The beaming effect effectively puts the burst on a cosmic loudspeaker, but one that only broadcasts in two very specific directions. This also explains why gamma-ray bursts are so rare from our perspective. For us to see one of those narrow jets has to be pointed almost directly at Earth. We are, in a sense, winning a cosmic lottery where our planet must be in the precise line of sight of this celestial death ray. The vast majority of gamma-ray bursts happen in galaxies far, far away, but their jets are pointed in some other direction, completely invisible to us. This means that for every burst we detect, there are hundreds or even thousands of others that we completely miss. The universe is likely filled with these cataclysmic events, but we only witness the select few that scream their final message directly into our telescopes. While the initial flash of gamma rays announces a burst's arrival with unimaginable ferocity, it's incredibly brief, often vanishing in mere seconds and leaving behind a crucial mystery. Where exactly did it come from? The answer to that question isn't found in the gamma rays themselves, but in what follows a slowly fading, multi-wavelength echo known as the afterglow. This lingering signal is the true treasure for astronomers, transforming a fleeting, enigmatic flash into a detailed cosmic event we can study for weeks or even months. Think of the initial burst as a sudden, blinding lightning strike that illuminates the sky for a split second, leaving you disoriented. The afterglow is the lingering rumble of thunder that follows. It lasts much longer, and by listening to its direction and how it changes, you can pinpoint exactly where the lightning hit. This spectacular light show across the electromagnetic spectrum begins moments after the gamma rays subside. The narrow, relativistic jets that produced the initial flash are still plowing outward at nearly the speed of light, but now they're smashing into the tenuous gas of the interstellar medium that surrounds the dead star. This violent collision is like a celestial traffic jam occurring light years away from the original explosion. The material in the jet slams into this gas, creating a powerful shock wave that heats the material to incredibly high energies. This process acts like a massive natural particle accelerator, causing the shocked material to radiate profusely, first in X-rays, then in visible light, and finally as longer wavelength radio waves. This cascade of emission, slowly fading over time, is the afterglow we detect. Capturing this afterglow is a meticulously coordinated global effort. The moment a satellite like Swift or Fermi detects a burst, it instantly relays the rough coordinates to a network of robotic telescopes on the ground and observatories in space. These telescopes, from the Chilean deserts to the peaks of Hawaii, automatically swing into action, searching the predicted patch of sky for that new, fading point of light. Finding it is the key to everything. Once they have a visual lock on the afterglow, larger telescopes, like the Hubble Space Telescope or the Mammoth Keck Observatory in Hawaii, can move in. They don't just take pictures, they use spectrographs to break the afterglow's light down into a rainbow-like spectrum. It is within this spectrum that astronomers find the telltale signs of redshift, the definitive measurement that reveals the burst's colossal distance and its place in cosmic history. Without this persistent multi-wavelength afterglow to act as a celestial road sign, these most distant bursts would remain nothing more than mysterious, unlocated flashes in the deep, dark void. For decades, the hunt for gamma-ray burst afterglows was a frantic, often unsuccessful race against time. Astronomers knew these fading signals held the keys to understanding these explosions, but the initial gamma-ray alerts from older satellites were too slow and too imprecise. By the time the coordinates were manually processed and relayed to ground telescopes, the precious afterglow had often already faded into oblivion, especially for the short-lived bursts. What was needed was a new kind of mission, one designed not just to detect but to instantly react. That mission was NASA's Swift satellite, and its arrival in 2004 fundamentally changed the game, turning burst chasing from a speculative gamble into a precise science. Named for the bird's remarkable ability to swiftly change direction in mid-flight, the spacecraft was engineered with one primary purpose: speed. From its polar orbit high above Earth, Swift doesn't just wait for bursts to happen. It constantly scans the sky with its Burst Alert Telescope, or BAT. The moment the BAT detects a flash of gamma rays, the entire satellite springs into action with breathtaking autonomy. Within seconds, it calculates the burst's precise location and then performs a rapid slewing maneuver, literally pivoting its entire structure in space to point its two other onboard telescopes directly at the source. This incredible feat of robotic agility happens without any human intervention, a critical advantage when every passing second means a fading afterglow. These two other telescopes, named XRT for X-ray telescope and UVOT for ultraviolet/optical telescope, are the mission's workhorses. They immediately begin collecting data across multiple wavelengths, capturing the crucial early moments of the afterglow that had previously been lost. The XRT can pinpoint the location of the burst with an accuracy down to a few arcseconds. That's like identifying a single grain of sand from several miles away. This incredibly precise location is then instantly broadcast as a digital alert to observatories all over the world and even to other satellites in space. This automated alert system, known as the GCN, or Gamma Ray Coordinates Network, transforms global astronomy into a single, coordinated organism. Within a minute of the initial flash, professional and amateur astronomers alike receive a text message or email with the exact celestial coordinates, allowing them to train their instruments on the target faster than ever before. This revolutionary speed and precision are the reasons why we have been able to discover and confirm the most distant gamma-ray bursts in history. Before Swift, catching the afterglow of a burst from the cosmic dawn was a matter of pure luck. With Swift, it became a reliable process. The satellite's rapid response ensures that the optical and infrared afterglow is caught while it is still bright enough for the world's largest ground-based telescopes to perform follow-up spectroscopy. It is this spectroscopic data that provides the redshift measurement, the gold standard for determining distance. In essence, Swift acts as the universe's most efficient emergency dispatcher, sending out the exact address of a cosmic catastrophe so that other observatories can rush to the scene, gather evidence, and piece together what happened. Without this nimble satellite, bursts like GRB 090423 would likely have remained just another faint, unremarkable flash in the data, their profound secrets forever locked away. But the record for the most distant cosmic cataclysm is a title that is fiercely contested, and for a time, another incredible burst emerged as a challenger to the throne. Just 2 years after the discovery of GRB 090423, another flash of gamma rays was detected that would push our view back even further into the primordial darkness. Its name, GRB 090429b, reveals it was detected just 6 days after its famous predecessor, but its story is uniquely its own. Detected by the ever-vigilant Swift satellite in April 2009, this burst immediately presented a puzzle. Its afterglow was exceptionally faint and faded so rapidly that it vanished before the largest telescopes could capture a detailed spectrum, the definitive proof needed to measure its distance with absolute certainty. Without that crucial spectrum, astronomers had to rely on a more subtle, yet still incredibly powerful detective technique, photometry. Instead of breaking the light into a full spectrum to find specific shifted lines, they used powerful infrared telescopes like the Gemini North Observatory in Hawaii to measure the burst's brightness through a series of different filters, each sensitive to a specific narrow range of light. The results were astonishing. The afterglow was completely invisible in the filters that capture shorter wavelengths, but it suddenly appeared in the longer wavelength infrared filters. This sharp cutoff, known as the Lyman break, is a telltale signature of extremely high redshift. The light from the most distant objects in the universe is so stretched that the shorter wavelengths, which we see as visible light, are shifted far into the infrared part of the spectrum, making them invisible to optical telescopes. By meticulously analyzing this photometric data, the team calculated a photometric redshift of approximately 9.4. Translating that number into cosmic time places this explosion when the universe was a mere 520 million years old, a time even closer to the Big Bang than the epoch of GRB 090423. This new finding suggested we were witnessing the death of a star from a time when the cosmos was only about 3.8% of its current age. The implications were staggering. It meant that not only were massive stars forming in the universe's first 500 million years, but they were also already dying in these spectacular hypernova explosions, seeding the early cosmos with the heavy elements necessary for future generations of stars, planets, and even life itself. While the lack of a definitive spectrum means its distance title is held as a strong probability rather than an absolute certainty, GRB 090429b stands as a monumental testament to the violent and rapid pace of star formation in the universe's earliest chapters. Confirming the exact distance of these incredibly ancient bursts is one of the most challenging and high-stakes games in modern astronomy, a race against time that often hinges on a combination of cutting-edge technology, perfect weather, and a little bit of luck. The initial detection by a satellite like Swift is just the starting pistol. It tells us that something incredible has happened somewhere in the sky, but it doesn't tell us where exactly or how far away it is. To get that gold standard confirmation, we need a spectrum of the afterglow, and obtaining that is a monumental task. The first and most pressing challenge is the sheer speed at which the afterglow fades. For these distant bursts, the precious optical and infrared light that holds the key to measurement can vanish within hours, sometimes even minutes. This creates a frantic scramble. The Swift alert goes out, and astronomers around the world must immediately assess the target. Is it observable from their location on Earth? Is it above the horizon? Is the moon too bright? Are there clouds? Even a short delay or a single patch of bad weather can mean the difference between a historic confirmation and a missed opportunity. The most powerful telescopes in the world, like the Keck Observatory in Hawaii or the Very Large Telescope Array in Chile, are not simple point-and-shoot cameras. They are incredibly complex, heavily scheduled instruments that require precise planning to use. Getting time on them often requires a formal proposal submitted months in advance. To react to a random gamma-ray burst, astronomers rely on what's called disruptive or target of opportunity observations. This means they must literally interrupt another astronomer's carefully planned research to swing the massive telescope toward the new cosmic event, a decision that is not made lightly and requires immediate justification. And then there's the issue of brightness itself. A burst with a redshift of 9 or higher is so far away that its afterglow is incredibly faint, often pushing the absolute limits of what even these colossal telescopes can see. It's like trying to read the license plate of a car that's hundreds of miles away using only the faint glow of its taillights. The light is so scarce that collecting enough photons for a clear, usable spectrum requires long exposure times, sometimes hours of patiently gathering every single precious photon of light. All the while, the source is getting fainter and fainter. This is why photometric redshift, the method used for GRB 090429b, is often a necessary but less certain alternative. It's like identifying a color by squinting at it from a great distance. You can make a very educated guess that it's red, but without bringing it closer for a detailed look, you can't be absolutely sure of its exact shade. A spectroscopic redshift, on the other hand, is like using a high-powered microscope to analyze the exact pigments in the paint. It provides a definitive, unambiguous measurement. The relentless fading of the afterglow, combined with the logistical hurdles of using the world's most in-demand telescopes, means that for every distant burst we successfully confirm, there are likely several others whose secrets fade into the darkness before we can decode them. While we marvel at the raw power and incredible distance of these explosions, their true scientific value extends far beyond simply setting cosmic records. These distant gamma-ray bursts are far more than just spectacular fireworks. They are the most powerful natural flashlights in the universe, and astronomers have learned to use them as exquisite tools to probe the conditions of the ancient cosmos. When the brilliant flash of a burst erupts, its light does not travel through a perfect vacuum to reach us. Instead, it makes a 13 billion-year journey through the intergalactic medium, the sparse soup of gas and dust that floats in the vast spaces between galaxies. Every atom and molecule that light encounters on its way to Earth leaves a tiny fingerprint on it, and by carefully decoding these fingerprints, scientists can reconstruct a detailed picture of what the universe was made of billions of years ago. The process works much like analyzing the light from a distant lighthouse through a thick, patchy fog. The light from the lighthouse itself is bright and clear, but as it travels through the fog, water droplets absorb and scatter specific colors from its beam. By studying which colors are missing from the light when it finally reaches you, you can learn about the composition and density of that fog. A gamma-ray burst is the ultimate lighthouse, and the early universe is the fog. The burst's brilliant afterglow provides a pristine, bright background light source. As this light passes through clouds of primordial gas, elements like hydrogen, helium, and heavier metals absorb very specific wavelengths of light. This creates dark lines like missing pieces in a rainbow in the spectrum of the afterglow. The pattern of these absorption lines is a unique barcode that tells astronomers exactly what elements the light passed through on its journey. For the most distant bursts, this means we are analyzing the composition of the universe during the epoch of reionization, that pivotal period when the first stars and galaxies were burning away the primordial fog of neutral hydrogen that filled space. The light from a burst like GRB 090423 acts as a probe, slicing through billions of light years of this early material. By examining its spectrum, astronomers have confirmed that the universe back then was indeed much more primitive, with far fewer heavy elements like carbon, oxygen, and iron. The elements forged in the hearts of stars and scattered by their explosive deaths. The relative abundance of these elements in the absorption lines provides a direct measure of how many stars had lived and died up to that point in cosmic history. It's a way of taking a core sample of the universe, with each distant burst giving us a snapshot of a different depth, a different era, allowing us to build a timeline of how the cosmos evolved from a simple soup of hydrogen and helium into the complex, element-rich universe we inhabit today. These cosmic flashlights do their most critical work when we trace their path back to one of the most important and mysterious periods in all of cosmic history, the epoch of reionization. To understand why this era matters, we need to rewind the clock to a time before the first stars. For the first few 100 million years after the Big Bang, the universe was a relatively simple and dark place. It was filled with a thick, pervasive fog of neutral hydrogen gas. In this state, the hydrogen atoms are complete, with their electrons snugly bound to their protons. This neutral hydrogen gas is very effective at absorbing ultraviolet light, effectively making the early universe opaque to certain wavelengths and keeping it shrouded in darkness. This cosmic dark age didn't last forever. Something had to happen to burn away the fog and make the universe transparent to light, and that something was the birth of the very first stars and galaxies. Theorists call this transformative period the epoch of reionization. The term reionization itself is a bit of a historical artifact. The universe wasn't ionized immediately after the Big Bang, so it wasn't being re-ionized, but the name stuck. This was the process where the first incredibly luminous objects, those massive, brilliant population, 3 stars, and the earliest quasars began to flood the cosmos with intense ultraviolet radiation. This powerful UV light was the key. It was so energetic that it began to blast apart the neutral hydrogen atoms, stripping away their electrons and turning the gas into a soup of free-floating protons and electrons, a state known as an ionized plasma. Think of it like the sun burning off a dense morning fog. As these first sources of light ignited, they created ever-expanding bubbles of clear, ionized space around them. Over hundreds of millions of years, these bubbles grew, merged, and eventually filled the entire universe, rendering it transparent to light and ending the cosmic dark ages. This is the state the universe remains in today, but when exactly did this happen, how long did it take, and what were the specific sources of the ionizing radiation? These are some of the biggest open questions in cosmology. This is where the most distant gamma-ray bursts become absolutely indispensable. A gamma-ray burst from this era, like one with a redshift between 6 and 15, acts as a perfectly timed probe. Its light has traveled through this evolving landscape of ionization. By the time we capture its spectrum, that light carries within it the specific absorption signature of the hydrogen it encountered. By analyzing the precise patterns in this absorption, astronomers can determine what fraction of the hydrogen along that line of sight was still neutral and what fraction had been ionized at that specific moment in cosmic time. Each distant burst gives us a single data point, a measurement of the universe's transparency at a specific epoch. By collecting these measurements from bursts at different redshifts, we can start to chart the progress of reionization itself. It's like taking a core sample of the early universe at multiple depths. Did reionization happen quickly, driven by a sudden influx of brilliant quasars? Or was it a more gradual process powered by the collective output of countless early stars? The light from these ancient gamma-ray bursts, imprinted with the history of its long journey, is providing the empirical evidence we need to move from theoretical models to a concrete timeline of how the first light in the universe finally pierced the darkness forever. This prevalence of long gamma-ray bursts in the early universe points us toward a fundamental question: why were exploding stars so much more common back then? The answer appears to lie not just in the age of the cosmos, but in its chemical composition. It turns out that the very ingredients needed to make a star can also determine the spectacular way it dies, and this is where the concept of metallicity becomes absolutely crucial. In astronomy, metals refer to any element heavier than hydrogen and helium. This includes the oxygen we breathe, the iron in our blood, and the carbon that forms the basis of life. A star's metallicity, therefore, is simply the percentage of its mass that is made up of these heavier elements. Now, in the present-day universe, galaxies like our own Milky Way are relatively metal-rich, thanks to billions of years of stellar evolution. Stars have continuously fused hydrogen and helium into heavier elements in their cores, and then scattered them across space in supernova explosions, enriching the cosmic gas from which new stars are born. But the universe wasn't always like this. Immediately after the Big Bang, there were no metals at all. The cosmos was a pristine soup of about 75% hydrogen and 25% helium. The very first stars, known as population 3 stars, formed from this pure, low metallicity gas. They were true behemoths, thought to be hundreds of times more massive than our Sun, and they lived incredibly short, violent lives. Here's the critical connection. A star's metallicity has a direct and dramatic impact on its life cycle, and most importantly for us, its death. Metals in a star's atmosphere make it more opaque. This opacity increases the strength of the star's stellar winds. For a massive, metal-rich star, these powerful winds act like a constant, fierce gale, blasting its own outer layers back into space over its lifetime. This process steadily strips away mass, effectively putting the star on a diet long before it reaches its final days. By the time it's ready to explode, it has shed so much of its outer envelope that it may no longer have the sheer bulk and the specific internal structure required to produce the narrow, relativistic jets of a gamma-ray burst. It might still go supernova, but it will be a more spherical, less focused explosion. Conversely, a massive star born in a low metallicity environment, like those in the early universe, is a completely different beast. With far fewer heavy elements in its composition, its atmosphere is much more transparent. This results in significantly weaker stellar winds. The star can therefore hold onto its mass tenaciously throughout its entire life. It doesn't shed its outer layers. It remains a tightly wound, monstrously massive, and rapidly spinning object right up to the moment of its core collapse. This preservation of mass and angular momentum is the perfect recipe for a gamma-ray burst. When this star finally exhausts its fuel, its immense, intact mass ensures a catastrophic collapse, while its retained spin provides the necessary dynamics to form the accretion disk and channel the explosion into those incredibly narrow, energetic jets. This elegantly explains why we see so many long gamma-ray bursts in the distant past and far fewer in our local, metal-rich universe. The early cosmos was a perfect breeding ground for these spectacular events because it was chemically primitive. It provided the ideal low metallicity conditions for forging massive stars that could die in the most violently focused way possible. As the universe aged and became more and more enriched with metals, the conditions for creating these cosmic blowtorches became increasingly rare. So, when we detect a gamma ray burst from a redshift of 8 or 9, we are not just seeing a distant explosion. We are witnessing the final act of a star that could only have existed in the unique, metal-poor environment of the cosmic dawn. To grasp the sheer scale of energy we're discussing, we need to move beyond abstract terms and anchor it in numbers that, while still staggering, give us a foothold on reality. The preferred unit of measurement for these cosmic explosions is the erg, a tiny unit of energy in everyday terms. It takes about 1 erg to lift a grain of sand a millimeter off the ground. The total energy output of our Sun over its entire 10 billion-year lifespan is approximately 10 to the power of 51 ergs. A distant gamma-ray burst in a blast that lasts mere seconds can release over 10 to the power of 54 ergs. That is a 1 followed by 54 zeros. Let's break that down. 10 to the power of 54 ergs is a billion trillion times more energy than our Sun will ever produce. To put it another way, in those few seconds, a single gamma-ray burst releases more energy than our Sun will generate across its entire multi-billion-year existence. It is an output that defies human comprehension, a number so large it becomes almost meaningless without a dramatic comparison. If you could somehow capture and harness the total energy from just one of these distant bursts, it would be enough to power human civilization at its current rate for trillions upon trillions of years. It is an amount of energy that rivals the gravitational binding energy of an entire galaxy, meaning a single GRB has the raw power to nearly tear a galaxy apart. This is not just a powerful explosion. It is the single most luminous event known to occur in the universe since the primordial fireball of the Big Bang itself. And this measurement of 10 to the 54 ergs is what astronomers call the isotropic equivalent energy. This is a crucial distinction that takes the beaming effect into account. Remember, the energy isn't exploding outward in a sphere. It's focused into those incredibly narrow jets. The isotropic equivalent is a calculated value that asks, if this burst had exploded its energy equally in all directions instead of in focused beams, how much total energy would it have had to release for us to see the same brightness from Earth? It's a hypothetical number that allows us to compare the raw, underlying power of different bursts on an even playing field, and it is this number that reaches such mind-numbing magnitudes. This calculation reveals the true, terrifying engine at the heart of these events, an engine that, for a fleeting moment, outshines every star in its entire host galaxy combined and can briefly be seen across more than 13 billion light-years of expanding space. This search for the ultimate cosmic progenitor leads us to the most theoretical and tantalizing frontier in gamma-ray burst astronomy, the hunt for a signal from the very first stars to ever shine. These are not just any stars, they are known as population 3 stars, a hypothetical first generation of celestial giants that are thought to have been truly monstrous, composed only of the pristine hydrogen and helium forged in the Big Bang. While we have strong indirect evidence for their existence, we have never directly observed one, as they lived and died in the universe's first few 100 million years. Their ephemeral nature makes them the holy grail for cosmologists, and some of the most distant gamma-ray bursts we detect may be our best, and perhaps only, chance to finally find them. The case for a connection is compelling and rooted in the very physics that governs a star's death. As we discussed, low metallicity is the key ingredient for creating a gamma-ray burst, allowing a star to retain its mass and rapid spin. Population 3 stars represent the ultimate expression of this concept. They formed from gas that contained absolutely zero heavy elements. It was a perfectly pure primordial soup. This complete lack of metals would have resulted in exceptionally weak stellar winds, enabling these stars to grow to staggering sizes, potentially hundreds of times the mass of our Sun. Their titanic mass would have meant a ferociously short lifespan, burning through their fuel in only a few million years before collapsing directly into black holes. This combination of immense mass, rapid rotation, and absolutely zero metallicity creates what theorists believe would be the perfect engine for the most powerful long gamma-ray bursts imaginable. A confirmed detection of a population 3 gamma-ray burst would be far more than just a new distance record. It would be a direct window into the processes that ended the cosmic dark ages. The light from such an event would carry the unaltered spectral signature of the pure hydrogen and helium gas that surrounded it. We would see no absorption lines from heavy elements like carbon or oxygen because those elements had not yet been created. Finding this pristine fingerprint in the afterglow spectrum of an ultra-high redshift burst would be the smoking gun, providing incontrovertible proof that we are witnessing the death of a star from the universe's very first brood. So why haven't we found one yet? The challenge is immense. We are searching for a needle in a haystack of unimaginable size and age. Even if these stars produced incredibly luminous bursts, their extreme distance means their afterglows would be incredibly faint, pushing our very best telescopes to their absolute limits. Furthermore, the epoch of population 3 stars is thought to have been very brief, meaning such events would be exceptionally rare. Every time we detect a candidate burst from this era, like GRB 090423, astronomers perform a painstaking forensic analysis of its afterglow spectrum, searching for that telltale absence of metal lines. So far, none have shown this pristine signature conclusively. They all appear to have some level of metal enrichment, suggesting they are second-generation stars. But the hunt continues. With every new deep space mission and every upgrade to our ground-based observatories, we get closer to peeling back the final layers of time and catching a glimpse of the universe's first, most spectacular stellar fireworks. While our journey has focused on the long bursts from the deaths of colossal stars in the early universe, there is another, equally fascinating class of these explosions that tells a different story. Short gamma-ray bursts with their lightning-fast flashes lasting less than 2 seconds are the cosmic signatures of a completely different kind of cataclysm, the violent merger of 2 ultra-dense stellar corpses, like neutron stars or a neutron star and a black hole. Because these events require the previous existence of stars that have already lived their lives and exploded, they are inherently products of more mature, evolved galaxies. Think of it this way: a long burst is the death of a single massive star, a relatively quick event on a cosmic timescale. But a short burst requires 2 stars to be born, live their full lives, explode as supernova, leave behind stable neutron stars, and then slowly spiral together over billions of years before finally colliding. This lengthy process means that almost all the short GRBs we observe are relatively local, occurring in galaxies much closer to us in both space and time. This makes the hunt for a truly ancient short gamma-ray burst one of the most exciting and challenging quests in modern astronomy. Discovering a short burst with a redshift of, say, 6 or higher would be a monumental discovery, completely reshaping our understanding of early cosmic evolution. It would be like finding a sophisticated modern machine in an archaeological dig from the Stone Age. Its very existence would force us to answer a profound question: how could such a complex binary system form, evolve, and merge in such a short period after the Big Bang? The presence of a neutron star merger in the universe's first billion years would imply that the first generation of stars not only formed and died incredibly quickly, but also that their remnants somehow found each other and spiraled together at a pace far exceeding our current models. This could point to exotic and dense early environments where stars formed in tight clusters, making such cosmic dances more likely, or it might suggest entirely new pathways for binary star evolution under primordial conditions. The scientific payoff from such a detection would be immense. The merger of neutron stars is a prime source of heavy elements like gold, platinum, and uranium through a process called rapid neutron capture, or the R process. Confirming that this cosmic alchemy was happening in the very first chapters of the universe would provide a crucial piece of the puzzle for understanding the initial enrichment of the cosmos with the building blocks of planets and life. While the search for these ancient short bursts continues, their current scarcity at high redshifts itself tells a valuable story, painting a picture of an early universe dominated by the brief, brilliant lives of single massive stars, with the more patient, intricate dramas of binary mergers waiting for a later act to begin. Now, as we piece together the story of these distant explosions, we rely on more than just their incredible distance or brightness. We also use fundamental physical relationships that act as cosmic measuring tapes. One of the most crucial and intriguing of these is known as the Amati relation. Discovered by the Italian astronomer Lorenzo Amati and his team in the early 2000s, this is not a law derived from first principles, but an empirical correlation, a pattern that nature seems to follow, which we discovered by carefully observing many gamma-ray bursts. Simply put, the Amati relation reveals a tight, predictable link between two key properties of a gamma-ray burst: the peak energy of its gamma-ray photons and the total energy released in the form of gamma rays, what astronomers call the isotropic equivalent energy. In more technical terms, bursts with a higher peak energy, meaning their gamma-ray emission is concentrated at more powerful, higher frequency wavelength, are also the ones that release a greater total amount of energy. This correlation is beautifully consistent across a wide range of bursts, and it becomes an incredibly powerful tool for verification. When we detect a new, incredibly distant gamma-ray burst, one of the first things astronomers do is measure its spectrum to find its peak energy, and then use the Amati relation to estimate its total energy output. This predicted energy can then be checked against the energy we actually observe, which is calculated from its measured distance and brightness. For a burst that truly belongs to the distant cosmos, these two values align almost perfectly. It passes the test, confirming that its properties are consistent with other known cosmological gamma-ray bursts. This verification step is vital because it helps astronomers rule out potential imposters. There are other, much less energetic astrophysical phenomena that can produce brief flashes of gamma rays, but they would not obey this relation. If a supposed high redshift burst didn't follow the Amati relation, it would be a major red flag, suggesting we might have miscalculated its distance or that it was something else entirely. The relation acts as a cosmic seal of authenticity, providing independent evidence that a burst with a redshift of 8 or 9 is indeed a titanic explosion from the early universe and not a much weaker, nearby event masquerading as something grander. It's one of the key pieces of evidence that allows us to look at the data from a faint, ancient flash and say with confidence that we are truly witnessing the death of a colossal star from the dawn of time. Now, you might be wondering if the sheer distance of these ancient bursts somehow makes them last longer. It's a logical thought that light traveling for billions of years might get stretched out in time. But the incredible truth is that a gamma-ray burst's intrinsic duration is set at the source by the physics of the explosion itself. The duration we measure, whether a burst is short or long, has no direct correlation with how far away it is from us. We detect both brief, split-second flashes and dramatic, minutes-long events across a vast range of cosmic distances. The reason for this lies in the nature of the two distinct progenitor systems we've discussed. A short gamma-ray burst born from the hyperfast merger of neutron stars is an incredibly fleeting event by its very nature. That collision and the resulting jet production happen in a literal blink of an eye, typically lasting less than 2 seconds. This is true whether the merger happens in a galaxy 100 million light-years away or one that's 10 billion light-years away. The event is just as quick at the source. Similarly, a long gamma-ray burst stemming from the core collapse of a massive star involves a more protracted process of material collapsing and accreting onto the new black hole, which naturally produces a longer duration flash. The cosmos doesn't discriminate. It creates both short and long bursts in both the nearby and the distant universe. However, when we look specifically at the roster of the most distant gamma-ray bursts ever recorded, the ones with redshifts above 6 from the universe's first billion years, we notice a fascinating and telling pattern. Almost all of them are long-duration bursts. This isn't a trick of stretched light or an observational bias. It's a profound clue about the kind of stars that existed back then. The early universe was a factory for creating the perfect ingredients for long GRBs, monstrously massive, rapidly spinning stars with extremely low metallicity. These behemoths were primed to die in spectacular collapsar-style hypernova, which inherently produce those longer-lasting gamma-ray signals. Short gamma-ray bursts, on the other hand, require a much more lengthy and complex cosmic recipe. They need two stars to be born as a binary pair, live out their full lives, explode, leave behind stable neutron star remnants, and then spend perhaps billions of years slowly spiraling inward due to gravitational wave emission before they finally merge. This entire process simply takes more time than the early universe had to offer. While it's not impossible that a few binary systems could have formed and merged with astonishing speed in the dense environments of the first galaxies, their detection remains a major goal for astronomers. So, while distance doesn't determine a burst's duration, the dominant duration of bursts from the cosmic dawn tells a powerful story about the frantic, brilliant, and short-lived nature of the first stars to ever light up the darkness. The relentless pursuit of these cosmic milestones continues at a breathtaking pace, pushing our observational capabilities to their absolute limits and beyond. While we've been fortunate to catch a few fleeting glimpses of bursts from the universe's first billion years, the ultimate goal is to push even deeper to redshifts beyond 10, into an era just 200 or 300 million years after the Big Bang. This is the true frontier, a period when the very first stars were likely just beginning to flicker on, and detecting a gamma-ray burst from this epoch would be the equivalent of finding a fossil from the first few minutes of Earth's history. The challenge, however, is immense. At these distances, the expansion of the universe has stretched the light from a burst's afterglow so dramatically that it is shifted entirely out of the optical range and into the far infrared part of the spectrum, a region where our current telescopes have very limited sensitivity. This is where the next generation of astronomical marvels comes into play, led by the most powerful space observatory ever deployed, the James Webb Space Telescope. While not designed specifically as a gamma-ray hunter, Webb is arguably the most important tool ever created for following up on these ancient explosions. Its gigantic golden mirror and suite of exquisitely sensitive infrared instruments are perfectly engineered to see exactly the kind of light these ultra-high redshift bursts emit. When a satellite like Swift or its future counterparts provides the initial alert, Webb can rapidly turn to observe the afterglow, capturing its faint infrared glow with a clarity and depth that is simply impossible from the ground. Its powerful spectrographs can then dissect that light, searching for the telltale absorption signatures that will provide a definitive redshift measurement and, crucially, analyze the chemical composition of the gas in its immediate environment, potentially revealing the pristine signature of a true population 3 star. But the hunt doesn't stop with Webb. The future of gamma-ray astronomy itself is being shaped by ambitious new missions currently in development. Projects like the Space Variable Objects Monitor, or SVOM, a joint venture between China and France, are being optimized to quickly detect and locate high redshift bursts and alert other observatories with even greater speed. Further ahead, concepts like the Transient Astrophysics Observer and other dedicated missions are being designed with much larger gamma-ray detectors and more precise localization capabilities, increasing our chances of catching these rare events. On the ground, enormous new facilities like the Vera C. Rubin Observatory will continuously scan the entire visible sky every few nights, potentially discovering the afterglows of extremely distant bursts that other satellites might have missed. Together, this coordinated armada of telescopes represents our best hope for finally breaking the redshift barrier and capturing the light from a stellar explosion that occurred before the universe was even 2% of its current age, offering an unprecedented view of the cosmic dawn's very first moments. The relentless quest to catch and understand these fleeting cosmic explosions has done far more than just satisfy our curiosity about the early universe. It has fundamentally propelled the entire field of gamma-ray astronomy forward, driving a cycle of technological innovation and global cooperation unlike almost any other in science. The very nature of gamma-ray bursts, their unpredictability, their brief duration, and their incredible faintness at vast distances, has forced astronomers and engineers to become smarter, faster, and more collaborative. Each new record-breaking detection, each mysterious flash that fades before we can pinpoint it, presents a new engineering puzzle that must be solved. This has led to the development of increasingly sophisticated detectors on satellites, designed not just to see more, but to think for themselves. The evolution of satellite missions tells this story perfectly. Early detectors, like those on the Vela satellites, could tell us that something happened, but little more. The Compton Gamma Ray Observatory represented a massive leap, providing the first comprehensive map of the gamma-ray sky and revealing just how common these bursts were, but its localization was still too coarse for quick follow-up. This glaring need directly inspired the design of NASA's Swift mission, a spacecraft built from the ground up with one mantra: speed. Its ability to autonomously swivel and point its X-ray and optical telescopes within seconds of a detection was a revolutionary feat of robotics and software engineering, a direct response to the frustration of watching precious afterglows vanish. The success of Swift, in turn, set the new standard for what was possible, influencing the design of subsequent and future missions like the Fermi Gamma Ray Space Telescope, which provides a complementary wide-field view of the high-energy sky, and the upcoming Space Variable Objects Monitor, or SVOM, a mission designed through international partnership to be even more agile and sensitive. The most distant events, this technological arms race extends far beyond the satellites themselves. The challenge of analyzing the faint, red-shifted afterglow of a burst from the cosmic dawn has been a powerful driver for innovation in ground-based astronomy. It pushed for the development of more sensitive infrared detectors on the world's largest telescopes, like the Keck Observatory and the Very Large Telescope. It helped justify the need for the unparalleled infrared capabilities of the James Webb Space Telescope, which is now our most powerful tool for dissecting the light from these ancient explosions. The data from these events is so complex and rich that it has also driven advances in supercomputing and data analysis techniques, as researchers create increasingly sophisticated models to simulate the hyperphysics of a collapsing star or the propagation of a jet through the interstellar medium. Perhaps the most profound impact, however, has been on how astronomers work together. The fleeting nature of gamma-ray bursts has made international collaboration not just beneficial but essential. This necessity gave birth to systems like the Gamma Ray Coordinates Network, or GCN, a truly global notification system that instantly distributes the location of a new burst to observatories and scientists across the globe, ensuring that someone, somewhere under dark skies can point a telescope at it. This has created a unique, decentralized network where a discovery by a NASA satellite triggers observations by a telescope in Chile, data analysis by a team in Europe, and theoretical modeling by researchers in Japan. The study of these distant events has broken down geographical and institutional barriers, forging a worldwide community united by the goal of understanding the universe's most violent explosions. In striving to comprehend messages from the edge of time, We have not only advanced our technology, but have also learned to work together as a single planet-wide scientific endeavor. But with all this talk of universe-shattering explosions, a very natural and frankly terrifying question arises. Could a gamma-ray burst ever happen close enough to pose a threat to us here on Earth? It's a scenario that has fueled science fiction doomsday plots for decades, and the scientific reality is both reassuring and sobering. Let's break down the two critical factors that determine the answer: proximity and probability. First, the good news. The distant gamma-ray bursts we've been discussing, the ones from billions of light years away, are completely harmless to life on our planet. Their incredible distance acts as our ultimate shield. The intensity of any form of radiation, including gamma rays, follows what's known as the inverse square law. This means that its strength diminishes with the square of the distance. So, if you double the distance to a source of light, it doesn't just get twice as faint, it becomes 4 times fainter. Triple the distance and it becomes 9 times fainter. Apply this to a gamma-ray burst that's billions of light years away, and its apocalyptic power is diluted to an utterly undetectable whisper by the time its light finally reaches Earth. We can safely observe these cosmic cataclysms from the absolute best seat in the house, protected by the vastness of space itself. Now for the more sobering part of the answer. If a gamma-ray burst were to occur much closer to home within our own galaxy and pointed directly at us, the story would be dramatically and catastrophically different. A nearby burst, say within a few thousand light years, would be one of the most significant extinction-level events in our planet's history. The initial blast of gamma rays would deliver a devastating 1-2 punch to our atmosphere. First, it would violently rip apart nitrogen and oxygen molecules, creating immense quantities of nitrogen oxides. These compounds would act like a thick, dark curtain, dramatically darkening the sky and triggering a rapid global cooling, a gamma-ray winter, similar to the nuclear winter scenario but potentially more severe. Second, this chemical reaction would aggressively destroy the ozone layer, the protective shield that safeguards life from the sun's harmful ultraviolet radiation. With this shield obliterated, the planet's surface would be bathed in dangerous levels of UV light, causing widespread damage to the DNA of plants and animals and crippling the base of the food web in the oceans. The long-term effects would be even more dire. The energized gases in our atmosphere would likely combine to form a thick, toxic smog of nitrogen dioxide, which would fall as corrosive acid rain, further devastating ecosystems. The combined assault of sudden cooling, ozone destruction, and increased ultraviolet radiation would likely lead to a mass extinction event that could rival the one that wiped out the dinosaurs. So yes, the threat from a nearby gamma-ray burst is very real in a purely physical sense. However, and this is the crucial part, the probability of such an event is thankfully astronomically low. For a gamma-ray burst to be a true danger to Earth, 3 incredibly unlikely things all have to happen at once. First, a massive star in our galaxy must be poised to die in the specific type of hypernova that produces a long GRB, or a pair of neutron stars must be on the verge of merging to create a short GRB. Second, that event must occur relatively nearby, certainly within our galactic neighborhood. And third, and perhaps most importantly, the deadly jet must be pointed like a cosmic rifle shot directly at our solar system. Given the narrowness of these jets, the vast majority of bursts happen with their beams aimed harmlessly off into empty space. When we weigh all these factors, the odds are overwhelmingly in our favor. Statistically, scientists estimate that a gamma-ray burst capable of causing a mass extinction might occur within the danger zone of our galaxy only once every few 100 million years, or even less frequently. Furthermore, our region of the Milky Way is not a hotbed for the kind of massive, metal-poor, rapidly rotating stars that are the prime candidates for creating these explosions. We reside in a quieter, more metal-rich galactic suburb, which further reduces the already minuscule risk. So while the cosmic scales of power involved are humbling, we can rest easy knowing that the same immense distances that make these events so fascinating to study also serve as our perfect and permanent protection. This fading afterglow is the astronomer's equivalent of a treasure map, and its slow, predictable decay across different wavelengths of light unlocks a wealth of information that the initial flash could never provide. As the brilliant jet of material continues to plow outward at relativistic speeds, it slams into the thin gas of the interstellar medium, creating a series of complex shock waves. It's this ongoing collision, happening light years away from the original explosion, that powers the afterglow, causing it to radiate energy across the electromagnetic spectrum. But it doesn't fade all at once. The afterglow's behavior follows a distinct pattern, governed by the physics of the shock and the structure of the jet itself. In the first few minutes and hours, the emission is dominated by high-energy X-rays. Then, as the shock cools, the peak of the emission shifts to visible light, creating a fading point of light that can sometimes be seen with powerful amateur telescopes. Finally, the longest-lasting signal is often in the radio waves, which can persist for weeks or even months, providing a final, lingering whisper of the cataclysm. This multi-wavelength light curve is a rich source of data. By meticulously measuring how quickly the light fades in the X-ray, optical, and radio bands, scientists can deduce critical properties of the explosion and its environment. The steepness of the decline can reveal the geometry of the jet. Is it a narrow, tightly focused beam or a wider outflow? It can even tell us about the density of the surrounding gas. Was the star that exploded sitting in a dense stellar nursery, or was it in a relatively empty region of its host galaxy? A dense environment produces a brighter, more slowly fading afterglow as the jet has more material to collide with, while a tenuous environment leads to a quicker fade. Each wavelength tells a different part of the story, and by combining them, astronomers can build a remarkably detailed three-dimensional model of the aftermath of a stellar death that occurred billions of years ago. But perhaps the most profound use of the afterglow is as a backlight to study the burst's host galaxy and the vast cosmic web the light traversed. The brilliant, fading afterglow acts like a cosmic flashlight shining through fog. As its light passes through the gas and dust of its own host galaxy, and then through countless other galaxies and intergalactic clouds on its way to us, specific elements in that material absorb very particular wavelengths of light. This creates a series of dark lines in the otherwise smooth spectrum of the afterglow. Each set of lines is a unique barcode identifying the elements present: hydrogen, magnesium, silicon, iron, and their redshift tells us exactly how far away that absorbing cloud is. For a distant gamma-ray burst, this means we get a layered chemical history of the universe along that specific line of sight. We can see the composition of the burst's immediate environment, the interstellar medium of its host galaxy, and even the diffuse gas in the vast voids between galaxies. This turns a single, fleeting event into a powerful probe, allowing us to conduct a detailed chemical analysis of the cosmos at a specific moment in its history, all thanks to the precious, fading light of the afterglow. These incredibly violent explosions don't erupt in a void. Every gamma-ray burst has a home, a host galaxy where its progenitor star was born, lived, and died. And when we point our most powerful telescopes at the locations of the most distant bursts, what we find is utterly fascinating and completely different from our own cosmic neighborhood. The host galaxies of these ancient gamma-ray bursts are not grand, majestic spirals like our own Milky Way. They are, almost without exception, small, faint, and incredibly turbulent places, buzzing with a frantic pace of star formation. They are the building blocks of the universe we see today, and they offer us a direct look at the chaotic, fertile environments where the very first generations of stars were forged. To understand why this is so significant, picture a modern, well-ordered galaxy like our own. Star formation is a relatively slow and regulated process happening in localized nurseries within giant molecular clouds. Now travel back in time over 13 billion years. The host galaxies of that era were nothing like this. They were much smaller in size, often referred to as dwarf galaxies or proto-galaxies, and they were absolutely brimming with vast reservoirs of pristine gas, the raw fuel for creating stars. Without the heavier elements that help gas clouds cool and condense efficiently, the process was more chaotic and less efficient, but when stars did form, they tended to be monstrously large. These galaxies were cosmic pressure cookers, creating stars at a ferocious rate that puts any modern galaxy to shame. We call this the star formation rate, and for these distant hosts, it was often hundreds of times higher than the rate in the Milky Way today. This hyperactive star-forming environment is the perfect breeding ground for the kind of stars that produce long gamma-ray bursts. Remember, you need a massive, rapidly spinning star with low metallicity. These small, gas-rich, and chemically primitive galaxies provided the ideal conditions. Their abundance of fuel allowed for the quick formation of huge stars, and their lack of heavy elements meant those stars could retain their mass and spin. So, when we detect a gamma-ray burst from a redshift of 8 or 9, we are not just locating an explosion. We are pinpointing a specific type of cosmic factory, a galaxy that is actively under construction, furiously building its stellar population in the universe's earliest chapters. These hosts are so faint that their light is often completely washed out by the brilliant afterglow of the GRB itself, and it's only after the afterglow fades, days or weeks later, that we can even glimpse the faint, smudge-like galaxy that was home to such a titanic event. By studying the properties of these host galaxies, their mass, their size, their rate of star birth, we are essentially taking a census of the kinds of galactic environments that existed in the infant universe, helping us understand how the first structures coalesced out of the primordial darkness. But even with our most powerful telescopes, some signals from the edge of the observable universe remain frustratingly faint, pushing the absolute limits of detectability. This is where the universe itself offers us a helping hand through one of the most fascinating phenomena predicted by Einstein's theory of general relativity, gravitational lensing. This incredible natural process acts as a sort of cosmic magnifying glass, and it can occasionally transform an impossibly dim, ancient gamma ray burst into an object we can actually study in detail. The principle is rooted in the idea that mass warps the fabric of space-time. A massive object like a galaxy or a cluster of galaxies sitting between us and a distant GRB will bend the very path of the light rays coming from that burst as they travel toward Earth. This distortion doesn't just slightly shift the image. Under the right conditions, it can actually amplify the light, making the source appear significantly brighter than it would otherwise. Imagine trying to read the fine print on a distant sign with the naked eye. It would be a blurry, impossible task. Now imagine someone places a powerful magnifying glass between you and the sign. Instantly, the details are enlarged, sharpened, and brought into clear focus. A massive foreground galaxy cluster performs this exact same function for astronomers. When its gravitational field bends and focuses the light from a gamma-ray burst located directly behind it from our perspective, the result can be a dramatic brightening of the burst's afterglow. This amplification is a game-changer. A burst that would have been far too faint for our spectrographs to analyze might, through the grace of gravitational lensing, become bright enough for us to capture its redshift and dissect its chemical composition. This rare cosmic alignment does more than just brighten the signal. It can also create multiple images of the same event. The light from the burst can take slightly different paths around the gravitational lens, arriving at our telescopes at slightly different times. This presents a truly unique opportunity. By carefully studying these multiple, time-delayed images of the same afterglow, scientists can potentially learn more about the properties of the lensing object itself, such as the distribution of dark matter within the foreground galaxy cluster. It turns a single observation into a two-for-one deal. We get an amplified view of a stellar explosion from the cosmic dawn, and we also gain valuable insights into the invisible scaffolding of the universe that made that view possible. While lensed gamma-ray bursts are exceptionally rare discoveries, each one that is found offers a precious chance to peer even further back into time, revealing details about the earliest stars and galaxies that would otherwise remain forever hidden in the darkness. And this brings us to one of the most profound and chilling implications of these distant explosions, a concept that connects the violent death of stars to the haunting silence of the cosmos. It's an idea that places gamma-ray bursts squarely at the heart of one of astronomy's greatest mysteries, the Fermi paradox. This paradox, named after the physicist Enrico Fermi, simply asks a deceptively simple question. If the universe is so vast and ancient, and the ingredients for life seem so common, then where is everybody? Why have we seen no evidence, no signals, no artifacts of other intelligent civilizations? Gamma-ray bursts may provide a terrifying piece of the answer, suggesting that the universe might not be a quiet, safe haven for life, but rather a cosmic shooting gallery where cataclysmic events routinely sterilize vast regions of space. The logic behind this grim hypothesis is disturbingly straightforward. We know that a gamma-ray burst occurring within a few thousand light-years of a planet would likely trigger a mass extinction event, wiping out complex life and resetting the evolutionary clock. Now consider the early universe that we've been exploring. It was a far more violent and dangerous place than our present-day cosmos. The rate of long gamma-ray bursts was significantly higher billions of years ago, perhaps 100 times more frequent than it is today. This means that for the first several billion years of the universe's history, galaxies were regularly swept by these lethal waves of radiation. A planet orbiting a star in the habitable zone, patiently developing the complex chemistry of life, could have its progress utterly obliterated in a matter of seconds by a burst from a distant, dying star. Life might have arisen countless times across the galaxy, only to be systematically scrubbed clean by these periodic sterilizations before it could ever evolve to intelligence or develop a technological civilization. This concept offers a potential solution to the Fermi paradox known as the gamma-ray burst sterilization hypothesis. It proposes that we don't see other civilizations not because they don't exist, but because the universe has only recently become habitable for long enough stretches of time to allow intelligent life to develop and thrive without being interrupted. The frequent GRBs of the early universe acted as a kind of galactic regulation mechanism, a reset button that prevented any one civilization from gaining a multi-billion-year head start. We here on Earth may be among the first generations of intelligent life to emerge in a cosmos that has finally calmed down enough to allow for such a delicate, long-term experiment. Our solar system, located in a relatively quiet suburban region of a metal-rich galaxy, might have simply won a cosmic lottery, evolving in a bubble of space and time that has been fortunate enough to remain outside the lethal beam of a nearby burst for over 4 billion years. This idea transforms our perspective on these distant explosions. They are not just historical curiosities from the deep past, but may have been the decisive factor in shaping the potential for life itself across the entire cosmos. Looking forward, the next leap in our cosmic detective work hinges on a new generation of observatories specifically designed to push further into the high redshift frontier. Leading this charge is the Space Variable Objects Monitor, or SVOM, a mission born from a collaboration between the Chinese National Space Agency and the French Space Agency, set to launch in the coming years. SVOM is essentially a next-generation Swift, engineered with the specific goal of hunting the most distant and elusive bursts. Its suite of instruments is optimized for speed and sensitivity across a broader range of the spectrum, particularly in the crucial infrared window where the light from these ancient events is stretched. Its gamma-ray and X-ray monitors will not only detect bursts with incredible precision, but will also calculate their positions and broadcast alerts to ground observatories even faster than current systems can. Perhaps most importantly, SVOM carries a dedicated infrared telescope on board, a first for a GRB mission, allowing it to immediately begin studying the afterglow of high redshift bursts that are often too red and too faint for Swift's optical instruments to catch. This means we'll be able to capture the spectral fingerprints of these events during their earliest and brightest phases, dramatically increasing our chances of obtaining a definitive redshift measurement before the precious signal fades away. Beyond dedicated GRB hunters, a revolution in ground-based astronomy is also underway, poised to transform our understanding of these phenomena. The Cherenkov Telescope Array, or CTA, represents a completely different and incredibly powerful way to study the high-energy universe. Unlike satellites that detect gamma rays directly, the CT is designed to observe the secondary effects of the highest energy gamma rays as they interact with Earth's atmosphere. When these photons strike the atmosphere, they create a brief, faint flash of bluish light known as Cherenkov radiation. The CT will consist of over 100 telescopes spread across sites in Chile and the Canary Islands, working in concert to detect these fleeting flashes. While its primary goal is to study cosmic particle accelerators like supernova remnants and active galactic nuclei, its incredible sensitivity to the highest energy gamma rays could provide a revolutionary new window into gamma ray bursts. For the first time, we might be able to observe the highest energy component of a GRB's afterglow, revealing new physics about particle acceleration in the relativistic jets and potentially detecting emission from bursts at unprecedented distances that are too faint for current satellites to see. The true power of this future, however, lies in the symphony of collaboration between all these facilities. Imagine a scenario where SVOM detects a candidate ultra-high redshift burst and instantaneously relays its coordinates. The James Webb Space Telescope, already a powerhouse for afterglow spectroscopy, swings into action to capture its infrared spectrum. Simultaneously, the CTA, alerted to the event, scans the location for any ultra-high-energy gamma-ray signature. On the ground, the Vera C. Rubin Observatory, with its ability to survey the entire visible sky every few nights, might have already captured the rising light curve of the optical afterglow in its immense dataset. This multi-messenger, multi-wavelength approach, combining space-based and ground-based assets across the globe, will allow us to build a more complete picture of a single cosmic event than ever before. We won't just be measuring a distance, we'll be probing the physics of the jet, the structure of the magnetic fields, the density of the circumburst environment, and the elemental composition of the primordial gas it traveled through. This interconnected network of next-generation tools promises to turn each distant flash from a simple data point into a richly detailed chapter in the story of the early universe, bringing us closer than ever to witnessing the very first seconds of starlight. Even with all we've uncovered, the story of these distant explosions is far from complete, and some of the most fundamental questions remain tantalizingly unanswered. One of the most persistent mysteries is why some massive stars die in these spectacular, jet-driven gamma-ray bursts while others, of seemingly similar size, end their lives in more traditional spherical supernova. We understand the recipe requires high mass, rapid rotation, and low metallicity, but the exact proportions of these ingredients and the subtle physics governing the final moments of collapse are still not fully understood. It appears there is a critical threshold, a precise combination of angular momentum and magnetic field strength in the collapsing core, that determines whether a star can launch these relativistic jets. Imagine two stars that look nearly identical from the outside. one might possess just enough internal spin to form the necessary accretion disk, while its neighbor, perhaps stabilized by a hidden binary companion, does not. This fine line between a hypernova and a regular supernova is one of the great puzzles of stellar astrophysics, and each new gamma-ray burst we detect provides another crucial data point in solving it. This mystery extends directly into the primordial universe and the nature of the very first stars, the so-called population 3 stars. While we strongly suspect they were the primary engines behind the most distant bursts, we still don't know their exact properties. How massive were they truly? Theories suggest they could have been monsters, hundreds of times the mass of our Sun. But did they form across a wide range of sizes or only as extreme behemoths? What was their typical spin rate, and how did they form and distribute themselves within those first fledgling galaxies? A gamma-ray burst is the final, explosive signature of such a star, but it only gives us a glimpse of its death throes. We are left to reverse engineer its entire life and structure from that single cataclysmic event. It's like trying to understand the entire life cycle of a tree by studying only the pattern of its ashes after a lightning strike. We can infer a great deal, but the complete picture remains elusive. Furthermore, the entire initial trigger for the jet formation itself is still a subject of active debate and complex computer simulations. Is the primary driver of the jet the intense neutrino flux pouring out of the seething accretion disk? Or is it the powerful magnetic fields that are wound up to incredible strengths by the differential rotation of the collapsing star? Or is it some complex combination of both, a feedback loop where each process amplifies the other? Supercomputers around the world are running immense simulations, trying to model the fractions of a second when a stellar core becomes a black hole, to see which recipe successfully launches a jet that can punch its way out of the star. Each new observation of a burst's precise light curve and spectrum provides a real-world test for these virtual models, helping us refine our understanding of the fundamental forces at play during one of the most violent events in nature. These unanswered questions are not a sign of failure but a beacon guiding the future of high-energy astrophysics. They remind us that for every fact we cement into place, a dozen new mysteries emerge, each one more compelling than the last. The pursuit of these answers drives the design of new telescopes and satellites, pushing us to look deeper and with greater precision into the cosmic dawn. Every unexplained flicker in a burst's afterglow, every anomalous energy measurement, is a clue waiting to be deciphered. A whisper from the edge of time that challenges us to listen more closely and understand the universe's most dramatic moments of creation and destruction. Beyond their profound scientific importance, gamma-ray bursts have also ignited the public imagination, transcending the realm of astrophysics to become powerful symbols within our culture. These cosmic explosions have become staples of science fiction, serving as convenient and awe-inspiring plot devices for apocalyptic scenarios or as mysterious beacons from ancient alien civilizations. They appear in documentaries, novels, and video games, often portrayed as the ultimate expression of cosmic power and the sublime danger of the universe. This cultural footprint is fascinating because it reflects a deep, almost primal human response to the idea of such unimaginable forces at work in the void. A gamma-ray burst represents the ultimate what-if scenario, a natural disaster on a scale that dwarfs any terrestrial catastrophe, and this inherent drama makes it a compelling subject for storytelling. This resonance goes far beyond mere entertainment, however. The journey to understand these distant flashes is a powerful narrative in its own right, a testament to human curiosity and ingenuity. It's a story that begins with a top-secret military satellite program during the Cold War, evolves through decades of fierce scientific debate, and culminates in a global network of telescopes working in unison to capture the fading light of a dying star from the dawn of time. This narrative arc captures something essential about the scientific endeavor: the relentless pursuit of knowledge in the face of the unknown. The gamma-ray burst has become a modern-day celestial mystery, a cosmic cipher that we are slowly learning to decode, and in doing so, we are fundamentally rewriting our own origin story. Ultimately, the cultural impact of these events symbolizes a much larger and more profound quest, humanity's enduring desire to find our place in the cosmos. By striving to comprehend the universe's most violent and distant phenomena, we are not just collecting data, we are seeking context. We are trying to understand the forces that shaped our existence, from the forging of heavy elements in stellar furnaces to the potential threats that lurk in the galactic dark. Each detection of a distant gamma-ray burst is a reminder of both our insignificance and our incredible potential. We are tiny, fragile beings on a pale blue dot, and yet with our intellect and technology, we can reach across billions of light years to witness the brilliant death of a star that died before our world was even born. In bearing witness to these colossal events, we fulfill a fundamental human need to look up at the night sky, to wonder, and to understand the magnificent and terrifying universe we call home. From the accidental discovery by Cold War satellites to the record-breaking flashes of light that have journeyed for over 13 billion years, our exploration of the universe's most distant gamma-ray bursts has revealed a cosmos far more dynamic and violent than we ever imagined. We've seen how these titanic explosions are categorized into long bursts, the death cries of massive stars collapsing into black holes, and short bursts born from the fierce mergers of neutron stars. We've unraveled the mystery of their incredible distances through the cosmic redshift, a stretching of light that acts as a time machine, allowing us to witness events from when the universe was less than 1 billion years old. These aren't just abstract phenomena, they are fundamental to the story of our existence. They have acted as cosmic flashlights, their light piercing the primordial fog of the early universe, allowing us to study the epoch of reionization, that pivotal period when the first stars and galaxies burned away the darkness. They've shown us that the early cosmos was a perfect breeding ground for these events, with low metallicity environments allowing massive stars to retain their mass and spin, creating the ideal conditions for a spectacular, jet-driven death. We've explored the immense technological effort required to catch them, from the autonomous, rapid response capabilities of satellites like SWIFT to the global network of ground-based telescopes that work in unison to analyze their fading afterglows. The implications are staggering. The raw energy released in seconds rivals the total output of our Sun over its entire 10 billion-year life. The beaming effect funnels that energy into narrow jets, making them visible across the universe, but also meaning we only see the ones pointed directly at us. Their prevalence in the early universe even suggests a potential solution to the Fermi paradox, posing the chilling possibility that gamma-ray bursts may have routinely sterilized vast regions of space, preventing life from gaining a foothold until the cosmos grew older and quieter. Each fact intertwines with the next, painting a picture of a universe in constant flux, where death on a colossal scale paves the way for new creation. The heavy elements forged in these explosions and scattered across the cosmos eventually became the building blocks for planets and life itself. As we look to the future with next-generation missions like SVOM and the unparalleled power of the James Webb Space Telescope, we stand on the brink of even greater discoveries. We are closer than ever to potentially detecting the signature of a true population 3-star, the first generation of stellar giants, and to understanding the precise physics that triggers these universe-shattering jets. So the next time you look up at the night sky, remember that its apparent tranquility is an illusion. It is a canvas of incredible violence and beauty, of constant birth and death on a scale we are only beginning to comprehend. These distant gamma-ray bursts are more than just historical records. They are active probes, helping us write the story of everything. They remind us that curiosity is our most powerful tool, and that the pursuit of understanding, of peering back to the very edge of time itself, is one of the most profoundly human endeavors we can undertake. The universe is still whispering its secrets, and with every new flash of light, we learn to listen a little